Hello, this is Industrial Control Circuit Troubleshooting 2, 6 module. Now we are doing Genius Skill Test number 8. The work order that we received stated that the system recently behaved strangely. So what is the problem? Let's dive in. By visually checking the external devices and the circuit from the control panel and power panel, we find that there is one anomaly that happened at PLC input channel 2. Why? Because during idle condition, the LED status of PLC input channel load at channel number 1, 3, 4, 5 and 14 is supposed to energize and turn on. But channel 2 is not supposed to turn on under normal condition. By studying the circuit, okay, we know that this 2 is actually a drain. So maybe this drain switch having internally short circuit. So the current continue to flow into the path to energize PLC input load channel 2. That's why it's turned on. Or another reason maybe because there is an earth fault somewhere around this path. Okay, most of the time the earth fault happen between this line. Okay, so it also can be here because if there is earth fault here, the current will straight away go through this path and short circuit to earth. But one thing to note that if there is an earth fault happen here, because the earth has a very low resistance, it will cause short circuit. All the current will flow through this path and short circuit to curve, and no current will flow through this path and the other path, because all the PLC input channel has the load where the resistance is quite high at about 4000 ohm. So it's quite unlikely the earth fault happen, okay, before this switch. Most likely happen around this path or at the PLC input load. It will not happen here, because if it happen here, all the current will go through here and then will go to the ground. However, I do not deny the possibility there. So I will first check, okay, from drain switch point number 4 all the way to this wire. The easiest way is to check this one, drain switch to this wire first, that is before the load, and to check here at the load. This will be checked finally, because here is a bit tricky. These 4 load 1, 2, 3, 4 channel 0, channel 3 actually link together through the common line. Okay, just like this one, channel 0 to channel 3 is actually linked together after PLC input channel load to the common. Okay, so it's a bit tricky. So what am I going to do? I will first make sure there is no internally short circuit in the drain switch. Then I will check the earth fault from point number 4 all the way to here before the load. Then check the earth fault at the load. Okay, so drain 3, measure this is a input side using the DC voltage from power supply here. Okay, and then switch to DC voltage. Okay, you can put here or you can put here, 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 here also can, because all linked together. How I know? Because by looking at wiring diagram, this is an input side, this is from, okay, this all linked together, then finally go to the power supply, V negative, okay, negative voltage, right? Okay, so I will measure, okay, drain number 3. There's a voltage, so I test open it, still got the voltage. So what happened now? So that means it may be internally short circuit, so we had to cut off the power in order to check the resistance, because resistance cannot be measured live. Okay, so from drain 3 to here, okay, first we check whether it is internally short circuit. We have to measure the resistance across the switch, across the device. We want N open. However, it show open loop trigger to close, so the drain switch is actually functioning well. There's no issue. So most probably, if the switch is not internally short circuit, maybe it can be due to short circuit to earth, or what we call earth fault. So from this drain tree all the way to the PLC channel. Okay, PLC channel. This drain switch, drain push button number 3 all the way to TB23, all the way to TB23. You see this one from drain push button 3. So we can measure, so we can check the earth fault. As we know, to check the earth fault, the black probe or the multimeter always placed at the earth point to measure the earth fault. Okay, so now I measure this one. So measure earth fault, make sure 2 point is open circuit. Okay, this drain push button 3 linked to TB23 here, TB23 here. Okay, then we open here. For to checking whether the earth fault or the device internally short circuit, we have to have both end open. Okay, now this should give you open circuit, not resistance reading. As long as there's a reading, resistance reading, be it small or big, there's a earth fault. So we have to change this wire. Okay, now we solve the issue. Now remove the lockout takeout, and then you see the LED status at channel 2 is now off. This is the correct one. So we can run the process now. However, agitator is running. No. Okay. See, the agitator or MC overload relay trip. How we know? You see the overload relay button. If it's pop up, means there's trip. So normally close will be triggered to open. So we had to know that overload trip because there's an overload. Whether it's an electrical overload, mechanical overload, or process overload, we do not know. So at first try to check the electrical overload by measuring the current at the output of relay. If there's no current, that means there's open circuit in that particular phase. No current, no current, and no current. Now we having 3 phases do not have a current. So what is the issue now? So for these 3 phases, we can measure line to line voltage or phase voltage. If the line end is open circuit, like in this case, we can measure the phase voltage. However, if the line end is not open, it's actually closed, just like when this push button is in, that means we have to measure line to line voltage instead of phase voltage. Okay, otherwise it will give you the false reading. Okay, to check whether got any open circuit in the fuse. This fuse is okay, this fuse is okay, this fuse looks okay. So what is wrong with that? Okay, never mind. So we just cut off the power supply and perform the lockout takeout. Okay, then we measure the resistance across the device with one end open. Okay, this line is okay, this phase is okay, and then this phase is okay. Now we measure the line to line resistance of the motor stator winding. It's open loop, open circuit. Okay, this is okay. Open circuit, open circuit. That means this line is open circuit. Okay, so we know that this one, motor 1, this is the agitator, motor 1. Okay, it's a U side open circuit. This is agitator, so not necessarily open circuit, it can be loose termination, so we better check properly. So U side, okay, no loose termination. Okay, open loop, so we know if there's a problem. So we just change before we change inspect, some burn winding, so we had to replace. Okay, double confirm by measuring the line to line resistance one more time with one end open. Okay, looks fine, looks fine, looks very fine. Okay, now we can normalize all the wiring connection. Okay, normalize the multimeter and then remove the lockout takeout. Okay, then maybe we need to drain the water from the vessel. Okay, before that, try to measure the current from the overload relay outlet. Okay, 3.2 full load current. Motor running a 3.2 full load current. This is the correct way. So later we measure the heater conductor current. Okay, 21.6 looks like normal. One more thing I overlooked just now is the alarm. Okay, just now when the agitator, okay, turn on, agitator popping out, that means agitator is tripped. What happened is when this one trip, this normally closed auxiliary switch will be triggered to open. Okay, this auxiliary switch is here, number 4. Okay, we can see from the circuit diagram, auxiliary switch is channel number 4. Okay, channel number 4. Because of this is open, it is actually de-energized. So normally closed remain closed and it will come here and energize. Okay, it will come here then to energize this one. Then this virtual output is supposed to trigger the switch from normally open to close, and then it will go to energize the alarm. So in order to prove this, we can do a troubleshooting test. Let's say I cut off the main power supply. Okay, and maybe for this one, okay, I can simulate the single phasing electrical overload so that I will trip the overload relay and see whether the alarm is triggered. Because before that I don't see alarm lighting is on. Sorry, I need to download the program and we run again. You see, it's energized. Okay, when this overload relay trip, okay, the auxiliary switch which is connected as the normally closed will be triggered to open and then de-energize the circuit. Okay, this will be open. Okay, why open? Because normally closed, it will trigger to open when the overload relay trip. So this PLC input channel will be de-energized. What happened is input channel 4 normally closed will remain closed, so the current can flow through here and energize the virtual output. And you see the virtual output channel 0, virtual output channel 0 will be energized, and the LED at channel 0 PLC output channel switch will be turned on and the current can flow through this path. Okay, this one will be energized and LED will be turned on, and the internal PLC output switch, normally open switch, will be triggered to close, and the current can flow through this path and energize the alarm lighting. Alarm lighting is supposed to turn on, but in this case never turn on, so maybe the alarm having open circuit or the wire having open circuit along the line, or there's a loose termination. And one more thing is it must be able to reset, okay, the alarm. Okay, see, okay, Alarm is a channel 3. How I know? Okay, channel 3 alarm. When I press it, it will be de-energized. Okay, so the light will go off. You see? Okay, channel 3 light will be go off, and this one will be able to clear, provided the condition is fulfilled. Because now it's still tripped, so that's why there's current still here. So now I reset the breaker, and must be able to reset this one. Okay, it's able to reset. So okay, measure the resistance across the load. There's a resistance showing that it is okay. So this one to the alarm. Okay, the alarm. We know that this alarm connect to TB31 all the way to here. Okay, so from this point we measure resistance until here, TB31. Okay, measure this resistance across the wire. We want an open loop, so we had to change, okay, the resistance. Then remove the lockout takeout. Then we will run the process one more time. Okay, now alarm happened because I forget to connect back the wire, so I need to cut off the main power supply and perform the lockout takeout, and then normalize the wiring connection and reset the overload. Okay, then drain the fluid from the vessel, and then perform and rerun the process one more time. Okay, all right. Okay, the process is passed.